This video lesson corresponds with Section 4 of your thermochemistry online unit. We're going to finish up quickly Section 3, which finishes with a thing called Hess's Law, which talks about the additivity of heats generated in multi-step reactions. What we've been learning so far is that most chemical reactions seem like they're in a single step, but the case is not always true. In fact, most chemical reactions are multiple steps. They just happen so fast that it seems like one step. Let me show you an example. So we'll switch to the next slide, and notice this chemical reaction, which is the metal tin, metallic tin, reacting with chlorine gas to form tin 4 chloride, which interestingly enough is a liquid. This reaction is between three different particles, 2 molecules of chlorine and 1 atom of tin. And given the collision theory, it's highly unlikely that you would have 3 particles colliding at exactly the same time and exactly the same orientation to react. So what's more likely going to happen is that the reaction will take place stepwise. So the first step, shown here, is tin reacting with 1 chlorine molecule to form tin 2 chloride, and then tin 2 chloride will react with another chlorine if it's abundant enough to form our eventual product, tin 4 chloride. So back to Hess's law. Both of these stepwise reactions, as you can see here, are exothermic. The signs for delta H are negative. And the total heat then is the sum of the individual steps. So if both steps are exothermic, the total heat generated is equal to the sum of the individual steps. And that's Hess's law in a nutshell. In a multi-step reaction, the total heat generated or absorbed is additive, and that can include endothermic reactions. So if the first step is exothermic and the second step is highly endothermic, it's going to absorb all the heat generated in the first step and end up being an endothermic reaction. So let's do a little bit of math on this one. Let's go right back to our tin 4 chloride example. This is an easy one. You can add reactions, stepwise reactions, just like you add a math problem. So for example, you just go sort of vertically. So one thing to notice here is you've got a sort of master equation that you want to end up with, and we have 2 stepwise equations, step 1 and step 2. You can add these together. What I want you to notice, however, is a thing that's called an intermediate. Notice in the first step, tin 2 chloride is produced. In the second step, that same molecule, tin 2 chloride, is immediately consumed. That's called an intermediate, and we don't acknowledge it in the final summation of the 2 steps, because whatever is produced in the first step is immediately consumed. So anyway, we can add this up, and we'll end up with tin solid plus 2 chlorines. We add these vertical, 2 chlorine molecules is going to yield tin 4 chloride, SnCl4. And notice this equation is exactly like the one we are hoping to end up with, what I call the master equation. And now we can just very simply add these 2 heats together, and you end up with negative 511 kilojoules produced in that 2-step reaction. So both steps are exothermic, so of course the heat is additive. That's not always the case, though. So let me show you an example of something a little more complicated using Hess's law. Here is a reaction between aluminum metal and manganese 4 oxide, or manganese dioxide. And you yield aluminum oxide and the metallic manganese. This is very closely related to the thermite reaction. Instead of manganese 4 oxide, you have iron 3 oxide as the other reactant. In any event, we're given a couple of delta reactions of formation. Notice aluminum forming aluminum oxide, manganese forming manganese 4 oxide. And once again, I have a master equation that I want to always refer to while I'm doing the manipulation of the given equations. So I notice that in my master equation, that aluminum is on the left and aluminum oxide is on the right. And notice that this first equation, right, the first given one, has the same thing. Aluminum's on the left as a reactant, aluminum oxide's on the right as a product. However, we run into some problems when we look at the second given equation. The second given equation has manganese, the metal, on the left as a reactant, but we want it on the right as a product. So that's a problem, or is it? Remember, all reactions are reversible, at least in theory. So we're completely allowed to take this reaction, shown here, and turn it around, reverse it. Let me scroll up. So let's take this reaction right here. We're just going to cross it out, and we're going to reverse the reaction. We're going to say, let's say we take manganese 4 oxide, and we decompose it into manganese and oxygen gas. Okay? It's still going to have a delta H, but notice before the delta H, I'm just going to slide this line out of the way. The delta H before was negative, meaning this initial delta H of formation of manganese 4 dioxide is exothermic. Kind of makes sense. Combining with oxygen looks like a combustion, should be exothermic. If we turn that reaction around, though, you flip the sign of the original reaction. So now, to decompose this stuff, manganese 4 oxide, you'd have to add heat to drive off the oxygen. So now it's endothermic, and you flip the sign, and it's 521 kilojoules is the answer. So now we have almost gotten to the point where we can add up these two reactions. However, notice there's some coefficients that I have to worry about. For aluminum, I've got a 4 up here, I've got a 4 here, that's okay. Aluminum oxide, same thing. The manganese 4 oxide, however, and I need a 3 here, I need a 3 for the magnesiums, or sorry, the manganese is over here. So I'm just going to take this whole mess, I'm going to multiply it by 3, which means I also need to do that to the heat. I'm tripling the amount of material that I'm decomposing, so I got to triple the amount of heat added to do that. And when I multiply that, I get what, 1,563 kilojoules, and now I'm at a point where I can add up both of these reactions. So there are some intermediates, it looks like, to me. Looks like 3 oxygens is on the left in this initial reaction, 3 oxygens is on the right in the second reaction. And what I'll end up with is 4 aluminums. I'm just carrying these down. 3 manganese 4 oxides is going to yield 2 Al2O3 and 3 metallic manganese. Let me scroll down. Okay. And now I can add up these two heats. I have a negative exothermic part, and I have a positive endothermic part. And that's just fine. When I add those two together, I end up with a delta H of reaction, which is negative 1,789 kilojoules. So it's kind of like a logic puzzle. You have to look at what you want to get to. And again, the master reaction shown circled in blue is what you want to get to. How can I manipulate my two given equations to get to that when I add them up? That's Hess's law. All right, moving on. I want to talk a little bit about reaction spontaneity. So why are some reactions spontaneous? Why do they go forward without adding energy and others are not? Or some are so slow at existing temperatures that you need to give them a boost. Well, that's what spontaneity is about. Spontaneous reactions occur without adding any more energy. And a great example of this is rust. You know, you put your bike out in the rain, it's going to end up in rust. You don't add any energy, you don't have to heat it up. So that's a great example of something spontaneous. Most spontaneous reactions are exothermic. Remember, that's the third law of thermodynamics, that energy wants to run downhill. Nature wants to be in a lower energy state. So if a reaction is exothermic, giving off energy, it's going to tend to proceed to a more stable state, to a lower energy. But that's not always the case, and I'll show you a couple of demos of this when I get back, that there are some spontaneous endothermic reactions as well. So there's something else going on. That's shown here. Yeah, some reactions are endothermic. So a great example, which is not very exciting, is water evaporating. You know, you put a glass of water on your bedside table at 500 mils. The next morning it's going to be 470 mils. You're not adding any energy to it. You're not heating the glass up, and yet some of that liquid water has gone into the higher energy state, into the gas form. So why? What are the other driving forces besides energy change that might be doing that? And the answer is a thing called entropy. Now, entropy is kind of a unusual and hard to quantify measure of a system. What it measures is, you can think of it as randomness or disorder in a system. So how messed up something is. And a great example of something with low disorder would be a crystalline substance like diamond or quartz. Everything is locked in a position. You know where all the molecules are. You know what all the molecules are made of. And they have a low energy of motion. Whereas something that has high entropy would be like a mixture of gases at high temperature. There's all chaotic motion. You don't know where any single one is, only describable by probabilities most likely. So that's a system with high entropy. Now, reactions also tend to progress toward greater disorder. And this is actually the better definition of the third law of thermodynamics, is that energy runs downhill and disorder is the lower energy arrangement. You have to put energy in to things to make them highly carefully arranged. The great example of this, I like to think of my kid's bedroom. It's an unholy disaster most of the time. There's My Little Pony crap everywhere. There's you know, all kinds of music. There's books. There's dirty clothes. It's a disaster. To get it into an ordered state, we have to put energy in. It takes time and energy to put things away and clean up your room. However, you don't have to put much energy in to get it back into that unholy mess of a normal state. It just kind of happens by itself over time. That's not a perfect analogy, but it's a good idea of entropy. The symbol for entropy is capital S. Don't confuse it with lowercase s. Lowercase s is the specific heat of a substance for water, 4.184. And we're, of course, going to only be able to measure delta. And I'll be honest with you, here in Honors Chem, we're not going to measure or quantify delta S. I will give you that number. I'm more concerned that we know the meaning of it. So a positive delta S is a system that increases in its disorder. It becomes more chaotic from reactants to products in a reaction. And a negative delta S is the exact opposite, something that that gains order, that becomes less random across a reaction. So how do we predict that? Well, you can look at the state of the reactants versus the products to figure out if something has increased in disorder or randomness or it has decreased. So let's look at a couple of examples. A great one are changes in state. Let's say we're going from solid to a liquid, liquid to a gas, we're adding energy. It's also going to be a positive delta S. Certainly when we take a liquid like water and we boil it to a gas phase, we're radically increasing the amount of disorder in the system. So it's a positive delta S. And same with, you know, melting ice to the liquid phase. You're taking a highly ordered crystalline state, six-sided crystal, water, and you're melting it to a liquid water, which is chaotic in its molecular motion. So the amount of disorder increases. And then the opposite is true. If I take liquid water and I freeze it to a solid, of course we decrease the amount of disorder. So delta S is negative in that case. So changes in state are a great example, but that's not a chemical reaction. That's just a change in phase. If in a chemical reaction, the number, well, there's a couple of ways to tell change in order or disorder, so delta S. But the easiest way, and what we're going to focus on, is number of gas particles. This is just like when we were doing Le Chatelier's principle. Count up gas particles. And if the number of gas molecules increases, then the system has increased in disorder. So look at this reaction right here with decomposition of sulfur trioxide on the left. On the right, you've got sulfur dioxide and an oxygen molecule. So all we need to do is tally up the number of gas molecules. We've got 2 on the left as reactants. We've got 3 over here on the right as products. So even at the same temperature, there's going to be more disorder in the system on the right. So there's a positive delta S, an increase in entropy. Okay. Here's another one. 2 aqueous phase, meaning dissolved hydrogen peroxide molecules that decompose and form 2 liquid water molecules, no change in entropy there, but we do produce one gas particle, and that has chaotic random motion, so we've increased the entropy of the system. All right, so now let's think through a few of these, and I'm not going to quickly tell you the answer, but what if a gas is dissolving? So you've got a gas in the gas phase, the vapor phase, which is chaotic and random, and then dissolving into water, into the aqueous phase. So you have actually increased order or decreased disorder. So this is a negative delta S, a decrease in disorder, because now from a gas phase you've gone into a much more ordered system in a in a jar or in your desktop glass of water. What about a solid dissolving? Number 4 here. If you dissolve a solid, obviously you're going from a crystalline ordered arrangement to a highly disordered chaotic random arrangement. So you definitely have increased disorder there. It's a positive delta S. And then finally, even just heating something up. If you heat up a solid but you don't melt it, you still have increased the amount of vibrational energy of the molecules themselves. So there is more disorder in the system when something is warmer versus something that's cold. So that's also an increase in delta S. Let's do 2 or 3 on this page, and then I'll leave the rest of them for you guys to figure out. How about we do 1, 3, and 5? So first reaction, looks like we have decreased the amount of gas in the system as we've formed chlorine trifluoride. And again, just count the gas molecules, 2 on the left, 1 on the right. That means I've decreased disorder. So that is a negative delta S. Let's do number 3. That is dissolving methanol in water. So here we have a pure phase substance, highly ordered. And here we have a mixture. Remember, aqueous means that it's a solution, it's a mixture. So we have increased disorder, positive delta S there. And then let's look at the very last one. And the very last one, it looks like on the left we have 3 gas particles, 3 gas molecules. On the right, just 1 gas molecule and a liquid. So I think we've decreased the number of gas molecules, meaning we've decreased disorder. So this is a negative delta S. So all this talk about entropy, what does it mean? Well, it looks like some reactions are driven by, well, all reactions, sorry, back up there. All reactions are driven by 2 things. We've talked a lot about exothermia, how that's a loss of energy of reactants to products. Nature likes to be in that low energy state. So reactions tend to go forward spontaneously if they're exothermic, but if they also increase disorder, have a positive delta S, then they also tend to go forward. So there are 2 things. And if we put them together into one piece of math, we might be able to do some prediction about whether a reaction will tend to occur or will not occur at all at certain temperatures. So can we predict reaction spontaneity? And the answer is, oh yes, we can. So let's talk a little bit about that. So this idea of being able to predict spontaneity is a concept that's called free energy. And free energy sounds like what it is. It's energy that's available to do useful work after a reaction. And it's not just dependent on how much energy is generated in a reaction, how exothermic a reaction is. Because you always lose a little bit of that generated energy, okay? So first of all, exothermic reactions, negative delta H, tend to provide energy to the surroundings. Let's take burning coal as a way to generate electricity from which you can do some work, okay? So burning coal is certainly exothermic, and all that energy that's produced, all that heat energy can turn turbines, or it can boil water to make steam and turn turbines to generate electricity. So we're doing work. So that exothermic reaction provides some energy to do the surroundings, provides energy to the surroundings to do a little work. However, always, 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 some energy is not recoverable. It goes into non-useful things, random molecular motion as an example, heat in other words. So any engine, whether it's coal burning power plants, or whether it's your gasoline engine in your car, always feels hot. And if it feels hot, that means it's escaping the engine to your hands, feels hot, and that is not recoverable energy. That is entropy. That is lost molecular motion that can't be used for anything useful. So we can combine these two things, the energy generated, delta H, minus the amount you lose to entropy that is not usable. And that is maybe the most important formula in physical chemistry, physics and chemistry combined. And it's called the Gibbs free energy formula. That guy is Josiah Willard Gibbs. He was a very famous chemist in the late 1800s, was the first doctorate of engineering awarded in the United States from Yale, and then he stayed at Yale for the rest of his career. Einstein called him the greatest living mind in American history, greatest scientific mind. So this is a giant in the history of science. And he created this, he discovered, elucidated this formula. Notice red box formula, you're going to need to know how to use this. Where we've got a new thing called delta G. And delta G is the Gibbs free energy. And I want you to look at what it depends on. It depends on two things. First, how much energy is produced in, let's say, an exothermic reaction. That's delta H, it's negative in exothermic. And how much do you lose? So notice that number is, okay, here's delta H, here's how much energy is produced in a reaction. And then we subtract the amount you lose to entropy, which does depend on temperature. Remember, warmer things have higher entropy. So the amount of usable or free energy depend on these two things, delta H, how much is produced, and then how much you lose, and that's non-recoverable to entropy. And by the way, notice temperatures in Kelvin. Don't forget the Celsius to Kelvin conversion, which is Celsius plus 273 is equal to Kelvin. Okay, don't forget that. So we now have a really important equation. And things we can predict. Using this equation, we can predict the spontaneity of a reaction. In particular, reactions are always spontaneous if delta G is negative. So let me, let's go back here. So if delta G is negative, reactions are spontaneous. Take a look at why. It will have to be exothermic. So this is a negative, this value right here. And if delta S is positive, so I'm going to use the green marker. If delta S is positive, if you're increasing disorder, if you're losing energy to entropy, that means this number is positive, delta S, but it's multiplied by a negative, so that this number is also negative, this overall term in the, let's make it in the big blue circle right there. And if this is negative and this is negative, that means overall delta G is negative. So that is always, always spontaneous, okay? So if delta G is negative, the reaction is spontaneous. It'll go forward without having to add any energy or do anything to the system. Whereas if delta G is positive, that means the system must gain energy for the reaction to occur. You got to put energy in. It's a lot like an endothermic reaction, but ignoring the entropy change. So that's a non-spontaneous system. And so let's look at an example of this reaction. Here's a decomposition of solid ammonium chloride into two gases. So notice we start with a solid and we decompose to two gases. So entropy is going to be a positive. Here's the question. Is this reaction spontaneous at standard temperature and pressure? I'll give you those values. They're right here, 0 degrees C and 1 atmosphere of pressure, which we'll learn about next unit. I would have to give you the values. First of all, the temperature is easy. You can convert that to Kelvin. So the temperature is 273 K. The delta H, it is endothermic. So this is an endothermic reaction. I have to add heat. In fact, remember, we can put the number here, 176 kilojoules plus this. So meaning endothermic, got to add to the reaction to decompose this to ammonia gas and HCl, hydrogen chloride gas. But as expected, the delta S is positive. Now those are some weird units for delta S. They're always in joules per Kelvin or kilojoules per Kelvin. And you'll see why in a minute. The temperature multiplied by delta S will cancel that Kelvin, and you'll have an answer in joules or kilojoules. Anyway, it is positive as we expect because we increase disorder, more gas in the system. Okay? And now it's just a question of plug and chug. Let's chunk these numbers into the Gibbs free energy equation. And when I do that, it looks like this. I know I'm going fast, but here's what you end up with as an answer, is positive 98 kilojoules, meaning there is no free energy in the system. Free energy is when it's negative. The energy is given off by the system, the chemicals. In this case, 98 kilojoules are required for the reaction to go forward. So you have to put some heat energy into the endothermia and into the entropy change. So it's definitely not spontaneous. And you can set up a little grid, and this is right out of your online unit, section 4, for the conditions you need for a spontaneous reaction to occur. So the things that are always spontaneous, remember, are exothermic, so negative delta H, and increase the entropy, positive delta S. Conversely, there are things that are never spontaneous. If it's endothermic, so notice positive delta H, meaning we have to add heat to it, and you're ordering the system, so it's a negative delta S. If you got to put energy in to get the reaction to go, and the product is more ordered than the reactant, it's never spontaneous. It will not go forward unless you add a ton of energy to it. Lots of reactions that we imagine as being reversible are only reversible if you put a whole bunch of energy in, and that's the idea behind it would have a positive delta H, endothermic, and a negative delta S. You'd be ordering the system. And that's it for this quick lesson, and I will see you all when I return.